draw that? I wrote the nice one. But then someone's.
All right,
I won't say who, but I'm quite mad.
all right, everybody. I think we're ready
Anyway.
to get started. Today. Okay, now we are ready to get started. Today we have the last seminar of the semester. Very exciting. And we have Bartolomeo Fiorini here to talk to us about testing gravity on cosmological scales. Bartolomeo recently finished his PhD at the University of Portsmouth and then joined us here as a postdoc in October.
Yeah.
So take it away.
Thank you, Rachel, for the introduction. So today I'm going to talk to you about testing gravity on cosmological scales, which is basically my long-term research goal. And yeah, so it's not done yet. I haven't constrained gravity yet, but I will talk to you about the progress, at least that I've done so far. Does it work?
Maybe you need to click on the screen.
First, we click on the screen,
Yes,
and
yes.
then it's gone. Let me check.
Does it work?
Yes. So first of all, why do you want to test gravity? GR works pretty well for the solar system. So what are the motivations to test gravity on cosmological scales? The first motivation is because it's not well tested, well constrained yet on cosmological scales with the large scale structures. There are other tests, but not yet with the large scale structure that are fully constraining. And so we want also to check that the large scale structure gives tight constraints on gravity. And what is the saying of the large scale structure on gravity? And then clearly GR is good, works really well in the solar system, but it's not UV complete in the sense that from a quantum field theory perspective, if you try to normalize the Einstein action, that action basically only containing the Ricci scalar cannot be normalized in a quantum field theory, in a standard quantum field theory scenario. Furthermore, the lambda CDM model, which describes our universe very well, is based on GR and is very successful, but it requires an exceptionally small value for the vacuum energy, which is a bit. We need to understand why, at least if it's the value. You want to be very sure that this is really vacuum energy, and modified gravity, in theory, would be a way to explain a cosmic acceleration without requiring dark energy or vacuum energy. Okay. Why do we want to use the large scale structure to test gravity? So because we believe there is a lot of information about gravity in the large scale structure. This is because the very homogeneous universe that at least maybe Charlie could argue that it was not so homogeneous. Maybe we don't have so much evidence for the dipole, at least of the CMB, but the CMB was a good proof, at least on small scales, that the universe was very homogeneous and isotropic to some extent in the early universe, when the universe was young. And so a redshift something like 1000, you have density perturbation of order 10 to the minus 5. On the other side, we can see that if galaxy surveys that we can collect with our telescopes show a different pattern. The galaxies align on filaments and are very clustered compared to the very homogeneous CMB that was in the early universe. In this cosmic web, the structure is normally called cosmic web, and it can be seen at a redshift between 0.1, 1 order of magnitude I'm talking about, and has density contrast of order unity, if not more. So how do we get from a very homogeneous universe to very clustered universe? Sorry, wrong way around. This transition can be explained in the context of embodied simulations. So if we use particles to describe the dark matter distribution in the universe, and we inform the distribution of this particle at the beginning of our simulation with the CMB information, then we can just let this set of particles evolve under the action of the solar gravity forces. And this is what happens. So the dark matter particles move towards the overdensities, and they cluster, they collapse, they form what looks much more similar to the large-scale structure that we see in galaxy surveys. Okay, so this is to say it's only gravity that amplifies, I mean, not only gravity, but gravity is the main responsible of the amplification of the very small density perturbation in the universe in the large perturbation that we see today. Okay. So if we want to test gravity, we also need to know what is not gravity. What are the alternatives to general relativity? The simplest extension of general relativity, referred to in the field as modified gravity theories, incorporate an extrascalar field, and they can be described with an action like this one. Is the extended Browns-Dicke formalism. You can use other formalism to describe this, but it's useful to understand this, the rest of what I'm talking about here. So you have a non-minimal coupling with the Ricci scalar. I don't know why I'm using this pointer like an umbrella, because I won't use the umbrella yet. So you have a non-minimal coupling, they are extended, generalized, kinetic term and potential terms, and then you have the actual quanta. So if you study some particular examples of these theories, they often incorporate nonlinear dynamics in the scalar field. So if you solve the Kleiner-Gordon equation for the scalar field, you can find for specific choices of this functional k and u, you can find the chameleon mechanism, which is a form of screening mechanism that let the theories. I mean, these screening mechanisms are important for modified gravity theories to evade sort of system tests, because the fifth force, which is carried by the extra scalar field, is not measured in our experiment in our laboratories. So, coming back to the chameleon screening, this is realized through a particular choice of the scalar field potential. And if you do the calculation, you notice that this is sensitive to the density of your local density in the universe. Another example of screening mechanism is the Weinstein mechanism, which achieves screening of the field force thanks to the derivatives of the scalar field. Nonlinearities in these derivatives of the scalar field. And if you do the calculation again, you find out that this is sensitive to the curvature of space-time. In any case, there are other kind of screening mechanisms that you can study. We know at least a bunch of them. But in any case, the point I wanted to make here is that the screening mechanism makes your modified gravity theory depend sensitively on the scales. So we need to be careful at doing things only on linear scales with modified gravity. Sorry, wrong direction again. Okay, so then if we want to use, let me check with the time. Yeah. So if we want to use galaxy surveys to constrain gravity or the light scale structure, if you want, we need to deal with galaxies, and galaxies are complex objects. They are biased tracers of the dark matter distribution, and this means that basically we cannot probe the dark matter density contrast, but what we can probe is the galaxy density contrast, which is related to the dark matter one, and to the matter density contrast through this bias term, this B, which can also depend, it definitely depends on redshift, and can also depend on the scale. Other complications are that we cannot directly probe the density contrast in each point in space and extract information from this. What we can do instead is using its endpoint functions, endpoint statistics, like the 2-point statistics that in real space is known as the correlation function, or the power spectrum in Fourier space. Or if you go to a higher number of points, 3-point statistics, or the bispectrum in Fourier space that we'll see later. These two, the power spectrum and bispectrum, will be the focus of our analysis. Furthermore, we observe galaxies not in real space, but in redshift space. And yeah, this complicates the situation a bit, but it's also an opportunity, because this interaction, this effect of the redshift, the fact that we can measure the redshift of galaxies instead of the radial distances, means that we are sensitive to the velocity of the galaxies somehow, and which affect the position. So our redshift space position S will be related to the real space position R through this term, which depends on the velocity parallel to the line of sight. What is transverse to the line of sight is not important. The parallel component is crucial. And this is a very well-known problem in cosmology, the redshift space distortions, which can be studied in separate scales. So on very large scales, you have a coherent inflow of matter towards the overall density, which produces a squashing in redshift space. This can be studied with the Kaiser model in linear theory, and you find out that your overdensity, galaxy overdensity in redshift space, actually, it's not just related to the dark matter overdensity through the bias, but also through a term which depends on the linear growth rate of structure, and mu square, which is the cosine of the angle with the line of sight of your K wave number, your Quebec. On the other end, on small scales, you have nonlinear motion of your galaxies. Matter is realized on the scale, so the motion of the velocity is large and is not coherent. It's kind of random velocity inside the small scales around your overdensities. This produces another effect, which is known as the finger of God's effect. And it produces an elongation of your structures along the line of sight. So large scales, linear scales, you have squashing of the structure. On nonlinear scales, you have this elongation. Yeah. Now, we are mainly theorists, but we care also about the data. So it's good that Euclid and Desi will provide us with an unprecedented volume of data about galaxies in the form of galaxy positions in redshift space, indeed. So the redshift of galaxies and the angular coordinates. To extract most of the information from these galaxy surveys, we need to compare those to synthetic galaxy catalogs, because the nonlinear scales are important, because there are a lot of complications that we saw before. So one of the best way to do this comparison is through direct comparison with the galaxy MOX. Through a complicated machinery that for now we don't, we just represent like this. Maybe later, if there is time, we can go and check what is that. To test gravity with your galaxy surveys, you need to produce synthetic catalogs in modified gravity theories, which, as we said, they are described by an extra force, a fifth force, whose dynamics is controlled by the screening mechanism, which require accessing the nonlinear scales to fully constrain the gravity theory. You can access nonlinear scales, but you need cosmological simulations. And normally, the standard of cosmological simulations are full embodied simulations that have very high time and space resolution, and they can solve the full scalar field equation both for the gravitational potential and for the scalar field of the modified gravity. But one problem of full embodied simulation is that they are computationally very expensive. Millions to billions of CPU hours for a single simulation. And an alternative to use an approximate, actually not, maybe approximate is not the right word, a semi-analytical scheme, which is the Cola method, which allows a speed up of a factor 100 to 1000 with respect to standard embodied simulations. But the pipeline to produce Galaxy MOX with the Cola method wasn't ready when I started this project, so I had to work on it. Okay, so yeah.
So maybe you're going to say, but Cola, so embodied, okay.
Yeah.
What does Cola do?
I will say in a few steps. Okay. So our pipeline. I'm going to talk about our pipeline now. Then if we have time, we can see the complicated machinery to compare Galaxy MOX and Galaxy surveys. Our pipeline is a 3-steps pipeline. The first step is using mg-Cola, which is a code, an extension of Cola and modified gravity, to simulate the dark matter distribution. This is an example of what the dark matter distribution looks like in the end of your simulation. In the dark matter distribution, you can find halos with a friend-of-friend halo finder, which links together particles that are closer than a certain threshold. And they are represented, the halos here, with these blue spots. Finally, we can use a halo compression distribution model to place the galaxies in our halos with a technique that I will talk about later, this halo compression distribution. And so we will place a certain number of central galaxies in the halos and satellite galaxies based on the mass of the halo. To validate the pipeline, what we've done is to look around the literature and find other simulations to modify gravity, because you need full embodied simulations to be sure that your results are correct. And we found this suite, the elephant simulation suite. And this also justified the models that we chose for the comparison, because the modified gravity, the full embodied simulations were available for these two models, F5 and NY. But these are interesting models because they incorporate this chameleon mechanism, which I described before, and this Weinstein mechanism in the case of N1. They have quite different dynamics, one sensitive to the density, the other one sensitive to the curvature. So it was interesting to see the effects of modified gravity on the simulation of these two streaming mechanisms on the large scale structure. And to have a baseline, we also produce a simulation in GR. It's not actually just one simulation, it was a set of simulation to increase the signal noise. So the validation, now I will go through the pipeline again, describing each of the steps, or the 3 steps, giving a bit of a description of the theoretical base of the steps, and the techniques used in each step, and also I will show you the validation by comparison with full embodied simulation. So, first step is producing the dark matter distribution with mg-cola. What is mg-cola? Now I come to your question. So, cola stands for comoving Lagrangian acceleration. This is a technique that basically starts from the initial guess of the particle position, which is this red line represented here, which is calculated thanks to the second order Lagrangian perturbation theory approach. So it's an analytical solution for your first guess. Then you try to connect your guess, which is very good on linear scales, but breaks down when shell crossing happens. So when the motion of your particles become nonlinear. And then you need another technique, an embodied technique, which is known as particle mesh technique, which takes care of the small scale physics. So displaces the particles from the 12pt solution to the actual position. When you take modified gravity into account, you have extra complexity because we have an additional scalar field, and this could spoil the speed up. Sorry, I forgot to mention that, I said this before, that for a simulation can achieve a speed up, a significant speed up with respect to the embodied simulation. But when modified gravity is taken into account, the extra complexity for the scalar field can decrease the speed up. But fortunately, we have a screening mechanism approximation that can solve this problem and let us run embodied simulation, color simulation in modified gravity in a similar time with the GR1s. We had a 2-hour discussion this morning about this point here that I'm not going through in this talk. So for the particle mesh part, so what you do is that you take your particles and you interpolate them on a grid, on a regular grid. This is to estimate the density thanks to the position of your particle, you estimate the density on this grid. And this allows to use fast Fourier transform, which is a very powerful technique to compute the forces. However, you need this grid to be 3 times finer than mean interparticle distance to get accurate heliostatistics. And so we use these settings. So what the results look like for the first step of the pipeline? We compared, to validate this first step, we compared the color results with the embodied results at the level of the dark matter power spectrum. Now you will see this summary comparison plot many times in this talk, so I will spend some more time on this one in such a way that you can then read them more easily. On the top left, I place this full signal in GR, in this case the power spectrum, and I compare the blue line, which is embodied, with the orange line, which is color. On the top right, I'm taking the ratio of these 2 signals to understand how well the color line reproduces the embodied one. And we can see that we have like few percent accuracy up to K of 1, the level of the dark matter power spectrum in GR. On the bottom 2 plots, I'm instead showing what is the effect of modified gravity on the signal that I'm talking about, in this case, on the power spectrum. So in the case of F5, okay, to talk about this signal, we refer to the signal as boost factors. And they are defined as the ratio of the signal and modified gravity with respect to that in GR. So in the case of F5, we see that we have basically, we recover GR on very large scales. Remember that the x-axis is K. So on the right, we have small scales, and on the left, we have large scales. So on large scales, we recover GR. This is due to the fact that your scalar field in F of R theories have a non-zero mass. So after a certain distance, the Compton wavelength associated to the field, to the mass of the field, it has no effect anymore. So the kick force doesn't reach. And so on large scales, we recover GR. Then you have non-trivial dynamics on nonlinear scales, which is well captured by Kola. You can see that the orange line reproduces well the blue line. In the case of N1, already on large scales, you can see departure from GR. And again, you have a non-trivial dynamics on the nonlinear scales. Kola also in this case reproduces well the embodied results. And so we are happy with the first step of the pi effect. And we proceed to the next one. Sure.
Why is the Kola suppressing the power at small scales?
You mean in the GR signal? Yeah, that's a good point. So Kola has lower resolution than the body simulation.
So it's the resolution thing, it's not from the way that you're holding the particles.
No, it's not actually. Yeah, you're right. So it's not the technique itself. The technique is not an approximate technique. It's the resolution that we use for this particular simulation that is limiting our. Sorry. No.
So the perturbation theory doesn't break down.
The perturbation theory breaks down much sooner, around 0.1.
Oh, but then you add in the embodied thing to some kind of add.
Yeah, that particle mesh part of the code takes care of improving the situation there. But depending on how fine is your grid, the particle mesh grid, this one, your force resolution is higher or lower. So the finer the grid and the higher the force resolution, and you can go then, to deeper in the nonlinear regime if you increase this.
So the Kola only deals with the part of the power spectrum or whatever, sort of 1 megaparsec or something like that, or more. It doesn't affect the positions, or it doesn't kind of initialize the positions of the particles at all. Is that?
No, sorry, I don't understand your question. Can you...
So, because the picture I had, I probably misunderstood what your slide said.
You're talking about
that you have some.
So your first guess will be wrong on the scale.
Okay, right. So your first.
But then you're updating your position, the position of the particles. Sorry, I'm messing everything with this. Your position of the particles with your particle mesh part, and that can be precise. You need to increase maybe the number of time steps as well as you increase the force resolution, but you converge to full embodied simulations if you do this procedure.
Okay. So the first guess from the perturbation theory that you choose for the kind of very large K doesn't matter. Then.
No, it doesn't matter. It's actually it's just helping. It's basically a different frame of starting your particle position. So tracking your particle position, but it helps at early times very much, where it is very accurate and it lets you have less time steps. But then late times, it's not important.
Okay.
You could also get rid of the velvety part and go only particle mesh somehow. Other question?
So in the following slide, let's say bottom left plot, if I was to be able to extend K up until solar system scales, I would see that these lines go back to 1.
Yeah, definitely.
And I cannot do that because of the resolution. Okay.
We are talking about 1 megaparsec over H here. 0.1 megaparsec over H is another important scale, which is the where you can divide non-linear scales on the right to linear scales on the left.
Yeah.
More or less, approximately.
But if the, sorry, if
Yeah.
the scale, so this is the very large scales, same stuff. In the middle deviation on very, very small scales, same stuff.
Yeah.
And yeah. But
In F5.
in the, yeah.
Here you have already on large scales, you have different.
Would this modified theory of gravity then explain lambda, like then explain the accelerated expansion to the job of
So
lambda?
this gravity theory was proposed to solve the problem of cosmic acceleration. I don't think it really does it. I think it's quite constrained to not explain the accelerated expansion at all. Maybe some 20–30% of the expansion, but that doesn't make sense. You still require dark energy or cosmological constants. So
But when you do this sort of thing, or you look at modified gravity theories, I mean, when I say you, I mean the community. Like, are you still looking for a theory that explains the accelerated expansion, or you're just like saying, let's say that the gravity is not GR, let's test it. But do you still have that in mind, or is it a bit like difficult to achieve?
it's I think it's very difficult to achieve starting from a pure theoretical perspective. Maybe if you can like study a wider class of gravity theories, and you can find particular example by looking hard in parameter space that work in the direction, but it's not easy.
Right,
It's
so
not
the
easy to explain cosmic acceleration at the moment.
So it's sort of, I'm not saying it in as a bad way, I'm
No,
just
no,
trying to understand.
It's
So
a
it's sort of like not as a motivation there anymore for looking into modified gravity.
I mean, it's still a modification because in some sense,
Motivation.
Yeah.
Yeah.
yeah. Because in some sense, your gravity theory can produce effects that are similar to dark energy, that are degenerate with dark energy on large scales. So you want even to constrain dark energy, know what is your modified gravity, to understand what degrees of freedom are the dark energy ones and the modified gravity ones instead, and how they differ.
Oh, I think of it is sort of template finding. So people tried to write down things that accelerated from first principles. We tried all the obvious things, they didn't work. So what we now do is by trying to understand how phenomenology of these kind of new degrees of freedom impacts clustering scales. If we can predict, or if we found a signature in that clustering scales, then that's like a spotlight which says, okay, this kind of class of theory seems to work. And then we would devote a lot more theoretical attention to those, and then maybe we'd understand how those could accelerate. But until we found that deep departure from lambda CDM, we've got no guidance where to look. So that's why these theories are still useful, even though they're not accelerating.
So just sorry to, maybe the question that I had in the same direction, which even modified theories of gravity still need dark energy, still need a lambda there. That's the whole point. You cannot get rid of the
So I'm not talking about all modified gravity theories. There are many, I don't know, even a fraction of those. But yeah, for the ones we are considering here, you still need some sort of fine tuning to explain cosmic acceleration. Yeah. Okay. Next step. It's finding halos, the bound objects in our dark matter distribution. So again, we use a friend of friend finder, which links together the particles, even at a threshold, a certain threshold distance. Then we, since scalar resolution, as pointed out, is limited in some sense, we cannot resolve, we call simulations, the internal structure of halos. We use some empirical prescription for this internal structure. I'm not gonna explain this in detail, but those are empirical relations that are found in high resolution and body simulations. In particular, they're found in body simulation in lambda CDM. So to extend this to modify gravity, and in particular in the case of F5, where screening is less efficient, we needed to take into account the effect of the fifth force on the halo profiles and the velocity of the structure inside the halo. And we did this with simple fictive formula that we calibrated in the elephant, so the body simulations in modified gravity. We validated also, we tested also the accuracy of COLA at the power spectrum level, the halo power spectrum level. So again, same plot as before, put the signal here. The ratio of column and body is plotted here, and we see that it's basically consistent with 1, so we are happy with it. In the case of the boost factors, we have a weak modified gravity signal in F5 and even weaker in N1. But again, COLA is consistent with few percent accuracy with embodied simulations.
Sorry.
Yeah.
You're cutting at 0.4
Yeah.
because of Sublines.
Yeah, in general, indeed, when you have dark matter particles, you have like billions of them in a simulation. When you find the bound structure of the particles, the number of your objects clearly reduces, so short noise is much more important. So yes, you have short noise of the scales, but also it's a scale where you start seeing the effect, the limitations of the COLA approach, of the limited resolution. And so, yeah, but you don't care too much about the small scales of halos because baryonic physics enters at this point. And we are only talking about full embodied simulation in, I mean, only dark matter only, or gravity only, if you want, embodied simulations, even in the full embodied case. So, yeah, we don't investigate baryonic physics here. Last step of the pipeline, predicting the galaxies inside the halos. We use another empirical model found in body simulations for the occupation numbers of the centric galaxies and satellite galaxies in terms of 5 parameters. So a lot of freedom in this model. So in this model, you place a central galaxy with a certain probability, which depends on the mass of the halo. And you can place more than one satellite galaxies. The satellites are actually modeled as a power law. And if you take, for example, a halo of 10 to the 15 solar masses of average on the right-hand side of this plot, it's gonna have a lot of galaxies. Okay, only 10 actually, but yeah, 10, 11 galaxies. But this is something closer to a galaxy cluster. If you go higher in mass, you will have galaxy clusters. Basically, you are trying to model these objects. Okay, as said, we have 5 HUD parameters. It's a great freedom. So to fix these parameters, want to ask a question now?
Just about this block, so just to understand if I understand it, if
Yeah.
I have a halo that is not very massive,
Yeah.
I will only have one galaxy,
Or even less. I mean, or even no galaxies at all.
or even no
It's
galaxy.
an integer number, but the probability that your halo of mass 10 to the 12 has one galaxy is very little.
Yes. Thank you.
Okay. To fix this freedom, we use a fictive procedure. Basically, we define a loss function in terms of the power spectrum multiples in redshift space. Then we try to reproduce a reference signal, clustering signal, that can be taken from observations, galaxy surveys, or from embodied simulations in our case, just to test the internal consistency of this method. And there is also weight for the number density of objects as you want in your file catalog as well. This is basically what we define, the loss function we define to tune the HUD parameters. And we validate this, the last step of the pipeline by looking indeed at the multiples of the galaxy power spectrum in galaxy space. So the monopole and the quadrupole in particular. And since we use the HOD freedom, I mean, we use the signal to reproduce, to tune the HOD parameters, it's not surprised that we recover good agreement, particularly the monopole in GR, we have agreement between power and body, and the modified gravity don't show any significant departure from GR, because this is reabsorbed in this HOD modeling, which is, yeah. So this is true for the monopole, but when you go to the quadrupole, the freedom in the HOD parameters is not enough to reabsorb all the difference between modified gravity and GR. So here we see some departure, which are different in the case of F5 and in the case of N1. In F5, you have a scale-dependent departure from GR, and you really need to go into the nonlinear regime if you want to constrain this gravity model. In N1, instead, already on linear scales, you can see significant difference with GR. So in this case, with Einstein screening, you may not need to go into the nonlinear regime to grow gravity with this approach. In any case, sorry, forgot to mention that color reproduces well these boost factors of N-body simulations. So even the first step of the pipeline is validated, and we are happy with it. See, the time is really okay. We have something like 5 to 10 minutes. Okay. Okay, so we have our pipeline. We can produce galaxy mocks with it. So finally, we went from this step to this one, this other one, and now we can focus on the complicated machinery that allows us to compare galaxy mocks with galaxy surveys. So how do we compare them? We said before we cannot just look at the density fluctuation position per position, but we need to go further, and we need to go to higher statistics. So 2-point statistics as the redshift space power spectrum that we just seen. But other statistics can help removing the degeneracies in the parameter space. So we've investigated an estimator for the for the real space power spectrum, starting from the redshift space multiples. We investigate the bispectrum and also the void galaxy cross correlation function. This gives you some probes that you can compare between galaxy mocks and galaxy surface, but the way you compare these probes is, in some sense, you need to make predictions of these probes really quickly. You can either use analytical models or emulators, in the case if you want to use the simulation approach. And then you can run your Monte Carlo analysis and infer your cosmological parameters and modify gravity parameters from your galaxy surface. So let's first focus on the probes. So I have actually a lot of slides for these probes, but I will just skip to the void galaxy section in the interest of time. Okay. So voids are underdense regional space. They are not empty, they are just underdense. And this is because also, yeah, clearly we observe not the dark matter distribution, so it's hard to tell where is clear a region of space when a region of space is clearly empty. But we observe the galaxy distribution, which is biased, so could be tracing well the dark matter, but even not. So in where you don't have galaxies, you could have a lot of dark matter. So how do you detect voids? Do you identify voids in your galaxy distribution? You first need to estimate the density, and then you need to look for the underdense regions. To estimate the density from a discrete distribution of traces, you need a clever technique. This is, for example, the Voronezh tessellation allows you to do such a thing. You basically associate to each galaxy a certain volume, the volume which is closer to that galaxy, and in each you divide the space in cells, and in each cell you can define, you can estimate the density as proportional to the inverse of the volume of the cell. So the larger the cell, the smaller the density in the cell. Once you have your continuous representation of your density field, you can look for the minima of this density field, and you can identify voids in different ways. One of the most used technique in literature is the watershed void finding technique, which associates to basically identifies voids as the catchment basins of your density field. And the separations, the watershed hypersurfaces of these catchment basins will be basically your cosmic web, your filaments, your walls, and so on. Once you have your voids, you can define a center of the void by looking at the four most central galaxies and finding the center of the sphere going through these four galaxies. And once you have your void center, you can stack voids based on their centers. And you can look at the distribution of galaxies around voids in a statistical sense. And you can find void profiles. And try to sketch this here. So I'm plotting the galaxies around different voids, studying one void at a time. The colors are not very clear, but basically for each different voids, I'm using different colors. And you can see that for each void, the distribution of galaxies is far from symmetrical. It looks quite random. But if you stack a number of galaxies large enough, a number of voids large enough, so in this case, 1,000 of voids, you can start seeing that the distribution becomes more spherically symmetric, and you can really study your and produce your void profiles. And this is what we've done to see what was the effect of modified gravity on these void profiles. And so here I'm not showing the GR part of the validation, just focusing on the modified gravity effects. And I'm focusing on three different profiles. The first one is the integrated Arcata density profile, which is telling you basically how much the density is enclosed in a sphere of radius r around the void center. Then you have the radial velocity of your galaxy, radial velocity profile of the galaxies around the void, and the velocity dispersion of those galaxies. In F5, we see very little signal apart from the velocity dispersion. In F1, instead, we have significant difference enhancement of the void profiles with respect to the GR. So we have modified gravity information in these three profiles. But why these three profiles are important? Because you can model them with an analytical model, which I summarize here. So these three profiles are important to link the cross-correlation function of voids in real space to the one in redshift space. And the way, so this is where they enter in the modeling. I'm not have the time. I don't have the time to go through the details of this. But you can see that you're modeling your velocity of galaxies as a radial velocity component plus a velocity component parallel to the line of sight. And this other velocity component is assumed to be random with a following a Gaussian distribution. The radial component instead depends on the linear growth rate of a structure. And this is where the modeling enters. I mean, the analytical model enters, and depends also on the integrated dark matter density profile. And this gives you a connection if you can measure the real space cross correlation function of void and galaxies, and the one in real space and in redshift space, and you try to link this one to the other, the real space one to the redshift space one using these profiles, you can infer on the value of the linear growth rate. So can we recover these also? This works in GR, it has been used for state-of-the-art galaxy surface analysis. Can we also use these in modified gravity theories? And the answer is yes. Simple. We can, and we get unbiased constraints on unbiased estimates of your linear growth rate, which is summarized by this line basically. The distance, this is the normalized distance of your inferred value with respect to the fiducial value, the reference value, normalized by the variance, your error on the estimate. So we are around 1 or below, so we are happy with the estimate.
So the F5 was missing there because it's scale dependent and the
That's a good
data is
point.
not
Yeah, I
scale
wasn't.
dependent.
F5 as a scale dependent linear growth rate. So it's non-trivial to define a linear growth rate for this, but for the scales of interest of voids, it looks like we can basically use the GR value. It's not very far from the GR value. It's reproducing the GR value rate. A point I forgot to mention, you don't need to take into account modified gravity theories in your modeling because of some cancellation that happened in this model. So even if N1 has all these different profiles, they actually compensate each other. And so in the end, it's not important to include modified gravity in your model. Okay, so we are done with the probes. You believe me that the other two also work really well. And it's time. Okay, I will quickly mention on this last part. So you can use models or emulators. We've seen how to use a model for the galaxy void cross correlation function, but you could actually just run your simulations and use an emulator instead to produce your void catalogs, and you don't need any modeling in that case. So what are emulators? Very shortly, they are they're interpolator. So you have a function which has a non-closed form in a high dimensional parameter space. So it depends on a lot of parameters. Can be the result of the function can be just a scalar value, but it depends on a lot of parameters. And you want to interpolate this function in this parameter space. So emulators are perfect for this. Are really what you should use. I mean, they are basically the same thing that you could. I mean, they are an extension of interpolators in some sense. So when you have a one-dimensional function and you use smoothing line to interpolate it to make your code faster, that's an easy problem. But if you go in either dimension, you need some more clever technique, and the neural networks can work really well for this. They are you can study them mathematically, and they are universal interpolators that work well with nonlinear function and high-dimensional parameter spaces. So to test this direction, I produce an emulator for the NDGP boost factor of the dark matter power spectrum. So to train this emulator, this neural network, I've produced 440, I mean, including the test set, more than 500 simulations to test this emulator. So for more than 400 to train it and more than 100 to test it. And with Call, it took very little, just 1 day. In 1 day, I had all my results. So the day after, I could train the emulator and now we can make predictions for the dark matter power spectrum in milliseconds instead of running a full embodied simulation that could take a billion of hours or million of hours to get the same signal. This is the great advantage. So this is why you need those for Monte Carlo Markov chain. A couple of things I want to comment on. So I remember Laura asked a question when Alessio was describing emulators about the principal component analysis. So I also performed this analysis, and it's very powerful because if you think of your data vector, it can have something like, in this case of the power spectrum, something like 80 beams, 100 beams, 1000, depending on how fine you be in your space and how deep you go into the nonlinearity. And so if you try to scatter your training set in the data parameter space, in your data space, basically. So in the case of, I think this was something like 80 beams, okay? You will have a 80-dimensional parameter space, which is hard to imagine, but you can study which directions in this parameter space contain most of the variance of the distribution. This is what is represented here. So in a two-dimensional projection of this very high-dimensional parameter space, you will have one direction which explains most of the variance, and the other one, basically, you are looking for the eigenvectors, right? Once you have those, and they, in my case, just two of them were explaining more than 99.99% of the variance of the distribution, then you can neglect all the others, and with just two numbers, you can produce these signals. This is the potential why principal component analysis is important, because instead of having this is the structure of the network. So 7 is the number of input parameters, your cosmological parameter, redshift, and modified gravity parameters. Then you have hidden nodes that do the computation, and then you have the output nodes. It would have been something like 80, but thanks to the principal component, it was just 2. So it's much easier for the neural network to guess the solution, find the convergence in this way. And okay, so
basically you're using your COLA simulations
yeah,
to train this emulator,
yeah,
to build this emulator, train it and test it. And then now you have something that in 1 second or whatever gives millisecond, like gives you out the
matter power spectrum.
the matter power spectrum that then you use to do your Monte Carlo.
Yeah.
Okay. Instead of just for each Monte Carlo, go and
running a full
it
simulation.
should be a full N body without COLA.
I mean, yeah, in theory, but yeah, if you have COLA, it would be a COLA simulation, which still would take hours.
Yeah.
And with a lot of cores, so in CPU hours, you go like hundreds of thousands. But yeah, with the emulator, it's just a millisecond. And yeah, so this brings me to the conclusions. I've shown you that we have an efficient pipeline to produce realistic mock RFC catalogs in modified gravity. Then we can make accurate theoretical predictions for the power spectrum, for the bispectrum, and for the point profiles. I haven't shown you actually these 2 points, but next time, probably. And finally, also that COLA can be used to train emulators for beyond the CDM cosmologies, as in the case of NDGP theory. Thanks.